right, welcome to Unit 3, Lesson 2 about probability of combined events. You can see we have quite a lot of lesson objectives here. We want to talk about how to represent a sample space using a tree diagram or a Venn diagram. We're going to select an appropriate counting strategy to solve probability problems. We are going to calculate conditional probabilities and specifically for dependent events, and then we are going to identify and prove when events are independent and or mutually exclusive. So we'll talk about that and those formulas and how to do that. I'm not going to do the warm-ups with you, so you can go ahead and pause now and try the 3 warm-ups and see if you get these 3 answers. You might want to write them in your notebook, try it on your own, see how you do, and then of course, look at the answer key if you're not sure, because it'll show you a little more work. All right, simple probability. So what is probability? Hopefully you've already talked about probability at some point in your life. You know that when you talk about chance or the likelihood of something to happen, you're talking about probabilities. You know, sometimes you're like out on a basketball court and you have a ball and you're like, hey, you say to your friend, what is the chance of me scoring this basket right now? You're just messing around, or maybe you're shooting a paper wad into a trash can and you're like, hey, what's the chance I'm going to make this? Your answer should be between 0 and 1, right? You might say, oh, you have a 50-50 chance, or if you're rolling a die, what is the chance I'm going to get a 5? Well, that's a 1/6 chance, right? There's 6 numbers. Each one has the same likeliness. So those numbers, those possibilities are between 0 and 1. 0 being that it's not possible. Like if you have a die from 1 to 6 and you say, hey, what's the chance of me rolling a 7? Well, it's not possible because you only either have a 1, 2, 3, 4, 5, or 6. Or if you say, what is the probability that I'm going to roll either a 1, a 2, a 3, a 4, a 5, or a 6, then you would say, hey, it's 100% because that's the numbers on the die. So we can talk about it in terms of percentages, or we can talk about it in terms of fractions between 0 and 1. So here's your little formula, which hopefully you don't need. Theoretical probability, it's the number of desired outcomes divided by the total number of possible outcomes. Like probability of rolling a 5 on a die, 1 5 out of the 6 numbers over 6 different number outcomes, so it's a 1/6 chance. Now this is also in your notebook, except here, notice we changed the notation. This is the AP Stats notation, so we thought we'd go ahead and adopt it. So it says the probability that an event A occurs is noted as this right here. So P is probability, and that's the event inside the parentheses. The probability that event A does not occur is called the complement. And so we would do A with what looks like an exponent of C, but that C right there means complement. And the probability of A occurring plus the probability of A not occurring is equal to 1, right? What is the probability of rolling a 5? That's 1/6. What is the probability of not rolling a 5? That's 5/6, because there's 5 other numbers that are not a 5, and 1/6 plus 5/6 equals 1 whole. Or you could find the probability of the complement then by taking 1 minus the probability of just that event happening, or probability of A. So I feel like I talked that really fast, but have a little moment. Hopefully that makes sense. If not, of course, always reach out to your teacher or someone up here or something and ask. So let's try example 1. It says, if a letter is selected at random from the letters in the word Tampanese, what is the likelihood that the letter is a consonant? Okay, so consonants and vowels, hopefully you remember what those are, right? Vowels, there's only 5 vowels in the 26-letter alphabet. They're A, E, I, O, and U. So everything else is a consonant. So here, Tampanese, we have 1, 2, 3, 4, 5, 6, 7, 8 letters. They're all different letters. There are 1, 2, 3 vowels, which means we have 5 consonants. So the probability the letter is a consonant is 5 out of 8. There are 5 possible choices, and there are of consonants only, out of 8 possible letters. So it's 5/8. Letter B says, what is the probability the letter is not a consonant. So to practice showing work and showing that you understand what this means, you would put a consonant and then complement of that, right? So this is not a consonant. Well, you could say that's 1 minus 5/8, or you could just count the number of vowels in there, which is 3/8. You're probably not going to show this work necessarily right now for this not so complicated problem, but that is what we might be thinking, right? The not a consonant is the complement, and so you would take 1 minus the probability of a consonant to get the answer. Or you could also think of that as a probability of getting a vowel. Finally, for letter C, it says, what is the probability the letter is a T or an S? So probability of a T or an S. Notation-wise, you could use the U. So U means or, right? And when you see that or, you should be thinking plus. So it's a probability of getting a T, or, which means adding the probability of getting an S. Well, there's one T and one S, so you're either thinking 1/8 plus 1/8, or you're just simply thinking 2/8. If you want to reduce that to 1/4, it's fine, but it is not necessary. All right, here we are going to do a lot of our objectives. We have the independent and dependent events. We have a tree diagram we're going to do with the follow-up question and getting our answers. So that's a lot of the objectives just covered on this one page. So it says, if two events A and B are independent, then the knowledge that event A has occurred has no effect on the probability of event B. When two events are independent, we can say the probability of A and B equals the probability of A times B. So this little intersection means and means multiplication to me. So that's why you have this multiplication sign, right? This is a union, which means or, and or refers to adding things together. So if events are independent, then we can find their probabilities by probability of A and B. A intersection B is probability of A times probability of B. If the probability of event B depends on whether or not event A occurred, then A and B are called dependent events. And we can use this notation, the probability of B given that A has occurred, right? And that's also known as conditional probability. We have a condition, B given that A has occurred. And so when you have a condition, your original sample space gets smaller. It's reduced as a result of that condition that was given. Also for dependent events then, the probability of A and B, right, isn't just probability of A times B, it's the probability of A occurring times the probability of B occurring given that A has already occurred. So it depends on whatever happened here with A. Now if I reshuffle this, right, I could divide each side by probability of A, then you would get this formula here, which is the condition, the probability of B given that A equals the probability of A intersection B divided by the probability of A. All right, let's do example 2. It says a box contains 3 yellow blocks and 7 green blocks. 2 blocks are randomly drawn from the box without replacement. Calculate the following. So part A I eliminated here, but part A was to draw a tree diagram, right? So we're going to go ahead and do that over here. I just wanted to have space over here on the right-hand side. So first I draw my first block. My first block could be yellow, or it could be green. If I look at my probabilities, there are 3 yellow blocks and there are 7 green blocks. So I have 10 altogether. So my probability of choosing a yellow block is 3 out of 10, and my probability of choosing a green block is 7 out of 10. I continue. I have to choose my second block. When I choose my second block, I'm either going to get yellow or green. So now that I've already chosen a yellow, right, then what is my probability of the second block being a yellow? So it depends, right? I have a condition. I have less blocks in the box itself because it says you're not replacing it. So there's only 9 blocks left, and in fact I just chose yellow, so there's only 2 out of the 3 yellows in there as well. So my probability of choosing a yellow for my second block is 2/9. My probability for choosing a green as my second block, well, again, it depends. I just chose my block for yellow, so there's only 9 blocks left, but all 7 green ones are still in there. So there's a 7/9 chance of me getting a green for the second one. And then I continue down on my other branches. I have a 7/10 chance to get a green the first time. Well, then that means all 3 yellows are still in there, but there's only 9 blocks left. And then now I only have 6 greens left in there and only 9 blocks altogether as well. So that's my tree diagram. Now, if I go out that tree, right, if I go out here, sorry, I'm trying to change my colors. If I get yellow, yellow, what is the probability of getting a yellow, yellow? Well, that's the probability of getting a yellow and a yellow. So that's 3/10 times 2/9, which is 6/90. What is the probability of getting a yellow first and a green second? Right, a yellow first and a green second. You would say that's the probability of getting yellow and then a green. So that's 3/10 times 7/9, which is 21/90. Again, because I'm saying and. How about the next one? What is the probability of getting a green first and then a yellow second? So probability of getting a green first and then a yellow second. Well, that's 7/10 times 3/9, which is 21/90. And then finally my last one, what is the probability of getting a green and then a green? So you would say probability of getting a green and then a green, that's 7/10 times 6/9, which is 42/90. Now, you didn't have to do all of this. You could have just went right to answering the questions, but I wanted to make sure that you understood when you go out the branches, you're saying the word and, so you're multiplying going out the branches. Now, when I answer these questions, particularly if I look, let's do the first one. It says, what is the probability neither block is green? Well, if neither block is green, that means they're both yellow. So yellow and yellow, well, I already did that. That was my very first result. So that's just 6/90. Now my second one is different. It says, what is the probability that one block is green and one block is yellow? It doesn't say the first has to be green and the second has to be yellow. It just says one is green and one is yellow. We had 2 different outcomes, right? So we could have had the first one being yellow and the second one being green. So probability of yellow and green, or the probability of green and then yellow. Well, that or means I'm going to take the 21/90 and I'm going to add the other one, 21/90. So you should get your overall answer to be 42/90. So now when I'm combining these results out here, I'm adding them together because it's this result or this one. So I add them up because of the word or. The last example, it says, what is the probability that the first block was yellow, given that the second one was green? So the first block being yellow, so I'm going to use this formula up here. It's a probability of the first being yellow and the second being green, divided by the probability that the second was green. So the probability that was first yellow and then green, well, there's only one option. That's this one right here, right? First one is yellow, second one is green. So that on my numerator, I'm going to go out here, is 21/90. Then I divide it by my second one being green. Well, when is my second one green? My second one is green here and green here. So I have 21/90, or I have 42/90. So I have 2 options there. Now, if this is a denominator of 90 and this is a denominator of 90, those are going to cancel. So I end up with 21 divided by, well, 21 plus 42 is 63. So you could say 1/3, or you could just leave it as 21/63. And that's it. All right, so let's see what the difference is between example 2 and example 3. We still have yellow and green blocks. looks to me, but looks like we have a little bit more in this third example. So it says a box contains 12 yellow blocks and 8 green blocks. We're also choosing more. It says 5 blocks are randomly drawn from the box without replacement. So 5 blocks. Okay, your gut might be, okay, I'm going to make a tree diagram. So this is going to be yellow or green, and then I'm going to go yellow or green, then I'm going to do yellow, green, yellow, green, yellow, green, yellow, green. That's only 3 blocks, so I'm going to have to keep going and going and going. That's a nightmare. So I'm going to stop. I'm going to say, nope, no tree diagram for me. I'm going to stop and ask myself, does the order in which I select those the blocks matter? No, the order doesn't matter. So you need to be thinking combinations, right? NCR. What is the probability that none of the blocks are green? Well, none of the blocks are green means we're going to have all yellow. So the probability that all of the blocks are yellow, well, there's 12 yellow blocks to choose from. We are choosing all 5 of them from the yellow blocks. But the denominator has 20 blocks altogether. So it'd be 12 choose 5 divided by 20 choose 5, right? Any 5 in the denominator versus all yellow for the 5 in the top. And I'm just going to leave it like that. I don't have my calculator. I'm just going to leave it like that. Next one. It says, what is the likelihood that 2 blocks are green and 3 blocks are yellow? Again, the order in which you select them doesn't matter, right? So 2 blocks are green. It could be green, green, yellow, 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 green, yellow, yellow. There's all kinds of combinations you could have, but it's combinations because the order doesn't matter. So the probability of 2 green and 3 yellow, well, again, we have how many green altogether? We have 8. We want 2 of them from the greens, and we want 3 of them from the yellow. So we have 5 altogether, and in my denominator, I have 20 choose 5. So it's 8 choose 2 and 12 choose 3 divided by 20 choose 5. Okay, the last one, what is the probability that the blocks are yellow given that the blocks are all the same color? So the probability that the blocks are yellow given that all the same color. So that's the probability of all of them being yellow. Okay, I was going to write it out. That's okay, I'm just going to erase this. So probability, oops, that's not an eraser. Probability that all are yellow is what? We have 12 yellow. We're choosing all 5 to be yellow, but all the same color means they could be yellow or they could be green. So the probability of yellow is 12 choose 5, or the probability that they're green is 8 choose 5. So that would be my final answer. If you plug it into your calculator, that's fine. Otherwise, you can just leave it like this. I just put parentheses here. It looks kind of funny. You didn't need that, so don't worry about it. Okay, to do example 4, it's very similar to example 3. It says 5 cards are drawn at random from a well-shuffled deck of 52 cards. What is the probability that the hand contains all hearts? Well, the order in which you select these cards does not matter. So you have combinations, you have the NCR, it's a probability, so you have a numerator, you have a denominator. So go ahead and pause and try this on your own, and then you can check back with me for answers, or you can check the answer key. All right, so all hearts A should have been okay. If you wanted all 5 cards to be hearts, we have 13 hearts in your deck of cards, so it's 13 choose 5, and then 52 cards altogether, so divided by 52 choose 5. Exactly 2 hearts means out of the 13, we are going to choose 2 of them to be hearts. That means we have 3 left over that could be not hearts, which is why we only have 39 cards, because we have to subtract all 13 hearts because we want exactly 2. So there's 13 to choose from. Subtract all 13 with 39 left over because the other 3 cannot be hearts. So it's 13 choose 2 times 39 choose 3 divided by 52 choose 5. Next one, exactly 1 diamond. There are 13 diamonds. We're choosing 1. Exactly 2 hearts. 13 hearts. We're choosing 2. Exactly one queen of spades. There's only one queen of spades in the deck. We want that queen of spades. But notice my subscripts, we only have 1, 2, 3, 4 cards that we've chosen. We need a fifth card. That fifth card cannot be a queen of spades, it cannot be a heart, and it cannot be a diamond. So how many cards are left? Well, we have to remove the 13 diamonds, the 13 hearts, and the one queen of spades. There's only 25 cards left to choose from. It can be any of those 25 cards. And there's one that we're going to choose, and that's divided by 52, choose 5. So that was a little trickier. And letter D is definitely a little trickier, and you need to be thinking about the complement when you are doing letter D. So it says, what is the probability that you're going to get at least one club? At least one club means you could have one club, or two clubs, or three clubs, or four clubs, or five clubs. So I said or. So do I want to have all of those numbers written, all those problems? It's like one club, two clubs, three clubs, or four clubs. That would be four different things I'm adding up. No, I could just do 1 minus the probability of no clubs. So 1 minus the probability of no clubs is way easier than adding the probability of one club plus probability of two clubs plus probability of three clubs plus four clubs, blah, blah, blah. It's way more complicated. So it's 1 minus the probability of no clubs. No clubs. There's 39 cards that do not have clubs. We are choosing 5 from those 39 cards. We don't care what they are. Divided by 52, choose 5. So this is easier than writing the probability of 1, and then you'd have 39, choose 4, divided by 52, choose 5. Or the probability of 2. So I have to keep doing all that, right, until you have all of them that are clubs. So you'd have to write out all 5 of those different things, or 4, I guess is what it is, but it's up to you. But this, again, is what we want you to do, and it's easier. All right, on to example 5. It says a game is played where a fair-sided die is tossed and then a marble is selected from a bag. If a 3 or a 5 appears on the die, a marble is drawn randomly from bag M. If any other number appears, a marble is drawn from bag N. Bag M contains 3 red marbles and 2 green marbles. Bag N contains 2 red marbles and 8 green marbles. So I hope, because we have 2 different scenarios that could happen, we're going to roll a die, and then we're going to go to bag M or bag N, and then we're going to get a green or red marble, that you're thinking tree diagram. What is the best way to tackle the problem? Is it combinations or is it tree? Hopefully you're saying to yourself, oh, definitely tree diagram. So I'm going to get you started, and then I want you to pause and just try the question on your own, right? So what do we have? You're either going to go to bag M or you're going to go to bag N. If a 3 or a 5 appears on the die, then you go to bag M. Well, that's a 2/6 chance that you're going to go to bag M. That means there's a 4/6 chance that you're going to go to bag N. Once you're in bag M, you're going to choose a red or a green marble. Once you're in bag N, you would choose a red or a green marble. For bag M, you have 3 red marbles out of 5 altogether, or 2 green marbles. We're going to do the same thing for bag N. There's 2 red marbles and 8 green, so there's a 2/10 chance here and an 8/10 chance here. You could have changed that to 1/5, 4/5, that's fine, or just kept it as tenths. So I would say pause here and try the rest on your own, and then check back with me. Okay, did you get 4/30 for letter B, 20/30 for letter C, and 4/20 for letter D? Hopefully you did. Bag M in green, that's 2/6 times 2/5 for 4/30. Green from either bag, well, you had to do M in green or N in green, or means add, so that we already found that. Probability, calculate the second one, we get 20/30. And then, of course, we have our conditional probability, so I used the formula. It's nice, you should show this work, because you might get points for that when you're taking your assessments. So the probability of getting bag M, given that it was green, so it's the intersection of M and bag M and green divided by all of the probability of green. Well, we had those two answers up here, right? This is the intersection. This is just green. So I put the numerator divided by denominator. The 30s cancel, so I just get 4/20. Okay, here are some formulas that you might want to remember. I think they're on the formula sheet as well. For independent and mutually exclusive events. So here we just have, in general, for any two events, A and B, the probability of A union B equals probability of A plus the probability of B, and then we subtract the intersection. Hopefully you're saying to yourself, oh, that's just the, here's my A, here's my B, right? If I took the probability of A, that's this entire thing. If I took the probability of B, that's this entire thing. Well, this part got counted twice, so I need to subtract it one time, right? Or I can just add these three numbers together to get the probability of A union B. That's whatever the probability is for A only, the intersection, and B only. Independent events, the probability of A intersection B is just probability of A times B. You could also use this proof of independence. If things are independent, then the probability of B should equal the probability of B given that A occurred, right? Those should be the same thing if they're independent of one another. Finally, mutually exclusive, if there's no overlap, then that means the events are mutually exclusive, right? If there's no intersection, then mutually exclusive. So the intersection equals 0. Let's apply those to these next questions. So again, you should be able to do this on your own, but I'll take you through the Venn diagram and then you can try to answer the questions on your own. It says 350 students were surveyed on which language classes they attended in elementary school. So again, you should have a number here. For Spanish, 150 students took Spanish. That's this entire box. 205 students took Mandarin. That's this entire, sorry, I don't know why I said box, circle. And then it said 25 took neither. So that's out here, right? They took neither Spanish nor Mandarin. So I'm going to fill that in first. This is 25. But then I'm going to have a number that's Spanish only, a number that's Spanish and Mandarin, a number that's Mandarin only, and these four numbers, 1, 2, 3, 4, have to total 350. All right, well, 25 of those 350 took nothing, so I'm going to do 350 minus 25, so I have 325 students left that have to fill in Spanish only, Spanish and Mandarin, or Mandarin only. If I look at these numbers, I have 150 for Spanish and 205 for Mandarin, but that 150 for Spanish is this entire, these two have to add up to 150, right? So if I call this A and this B and this C, well, I know A plus B has to equal 150, and then for Mandarin, I know B plus C has to equal 205, right? So then what does one of those have to equal? Well, 150 plus 205 is 355, but it needs to equal 325. So I have an overlap. How much do I have an overlap of? Well, hopefully you're saying to yourself, that's 30. 30, so B has to be 30. And if B is 30, then I know Spanish only is 120, because now my red circle totals 150. And then my yellow circle has to total 205, so C has to equal 175. So again, what did I do? I took the total number of students and subtracted the didn't take either, so I only have 325 for these three spots. My numbers 150 and 205 were too big. They were bigger than 325. That means I had 355 minus 325, an overlap of 30 students. So I put those 30 students in there, and then I figured out the rest with my system of equations here. So go ahead and pause and answer questions B through G and see how you did. All right, so check out the answers. Did you get 30 over 350 for Mandarin intersection Spanish? Did you get 200 over 350 or 20 over 35 for not Spanish? Spanish or Mandarin was 325 over 350. Mandarin given that Spanish, she should have gotten 30 over 150. Again, any of these fractions could have been reduced, or you could have put them as decimals, so check your calculator. If you have an equivalent to mine, it's fine. Are they mutually exclusive? No, there's not, because there's intersection, right? So you have people who did take Spanish and Mandarin, so not mutually exclusive. And are taking Mandarin and taking Spanish independent? No, they are not. You could have seen that those fractions do not equal each other when you test the intersection versus Mandarin times Spanish, so they are not independent. Okay, let's try number 7. You should be able to do this on your own, right? If you draw a Venn diagram to help you, maybe you don't even need the Venn diagram, but you should be able to do this on your own. It says that the probability of A is 1/2, so that's this entire circle, right? So that's A plus B, that's 1/2. If probability of B is 1/3, so that's an entire circle, B plus C is 1/3, then the probability of A union B is 3/4. So that means A plus B plus C has to equal 3/4. So if 1/2 is the entire red circle and 1/3 is the entire yellow circle, then we should be adding those up, right, and seeing what we get. And if that equals 3/4, then that means there is no B, there was no intersection. So I do 3 6 plus 2 6, which equals 5 6. 3/4, so that's 10/12, right? And I'm going to make this 12ths, that's 9/12. So this is too big, so that means my intersection is 1/12. Again, there's so many different ways to think about this. This is just my little way of doing it, but I'm using that formula, right? A union B is probability of A plus probability of B minus the probability of the intersection. So if I plug in the different values, this is probability of A, this is probability of B. A union was 9/12, so what is my intersection? My intersection then is 1/12. Are they independent events? Well, B is the intersection of A and B is 1/12. So does that equal the probability of A times the probability of B? Well, the probability of A is what? It's 1/2, according to this up here. It's 1/2. The probability of B is 1/3. So does 1/3 times 1/2 equal 1/12? That is a false statement, therefore they are not independent. All right, let's look at number 8. It says Sharon and Lisa share an apartment. Sharon cooks dinner 3 nights out of 10. If Sharon does not cook dinner, then Lisa does. If Sharon cooks dinner, the probability that they have pasta is 0.75. If Lisa cooks dinner, the probability that they have pasta is 0.12. And then we have questions that'll follow up. So what should we do to answer these questions? What strategy should we have here? Well, hopefully you are thinking tree diagram. We have Sharon and we have Lisa. The probability that Sharon will cook is 30% chance. The probability that Lisa will cook is then a 70% chance. Then from there, they each may or may not cook pasta. So we have pasta and then we have not pasta. We have pasta and then we have not pasta. The probability that Sharon will cook pasta is a 75% chance, which means not pasta is a 25% chance. The probability that Lisa will cook pasta is only a 12% chance, which means it's an 88% chance that she will not cook pasta. There is your tree diagram. The rest you should be able to get, so I'm going to leave you be. Go ahead and pause and try it on your own. All right, did you get these answers? Lisa and not pasta is 0.7 times 0.88, which is 0.616. Not pasta, that's going out, right? Not pasta. So we already did Lisa and not pasta, so we just have to add on Sharon and not pasta, so we get 0.691. And finally, what if they have pasta and Lisa cooked? So that's the intersection of Lisa and pasta, which is 0.7 times 0.12. And then divided by both pasta. Well, we gave not pasta, so we can just do 1 minus that, the complement. And then you should have ended up with 0.272. If you didn't get that, ask your teacher or check out the answer key. but I think this is kind of the same as the answer key, but maybe not. So check it out. Our last question. The Athletic Council decides to form a subcommittee of 7 council members to look at how funds raised should be spent on sports activities at the school. There are a total of 15 council members, 9 males and 6 females. What is the probability that the subcommittee will consist of exactly 3 females? Well, we want a subcommittee, has to be exactly 3. We are going to have 7 altogether. So we have 6 females to choose from. The order in which I select them doesn't matter, so I'm going to use combinations. I'm going to choose 3 from the females. I have 9 males to choose from. I only have 4 people left over, so there's 4 males. There were 15 people to choose from. I want a 7-person committee. This is it. You can use your calculator to calculate, or you can just leave it like this. And that is the last problem. See ya.